In this lecture, we'll be introducing you to the executable file formats used by Windows and Linux. So on Windows, we have what's called the Portable Executable, or PE, file format. Under Linux, it uses the ELF, or Executable and Linkable format. Both of these formats are essentially conveying the same type of information. It's just a different layout, different data structures that are ultimately used. In this lecture, we're going to be giving sort of a higher level overview of these two formats, but for more information, just a few simple Google searches, you should be able to find the detailed specs for both the PE and ELF. And this will get you into the actual data structures and fields that make up these file formats. And ultimately, it's that level of information that's used by the reverse engineering tools that you use, like disassemblers, debuggers. They will end up parsing that information to figure out, for example, where the entry point is to the code and what the different sections are, etc. So we'll start with the PE. Again, this is the Windows file format. All the different extensions that you see at the bottom of the screen are different types of executable files. So we have probably the most common ones that you're used to seeing, the XE, DLL, and other you may or may not be familiar with, the like .sys for device drivers and other objects. But all of these, which are executable, contain executable code, are going to be formatted using the PE format. .NET files are also PE files, but they also have a .NET header, which contains some additional information about the managed code portions of the program. But we're not going to really talk about .NET in this lecture. So two key concepts to understand is you'll see references to RVAs and VAs, or virtual addresses, when you're reading information about headers. So the virtual address, this is the address and object once it is loaded into memory. And there's a preferred base address for most executables, and so the loader will initially try to load at that address. If it can't and needs to load at a different address, well, then it will have a different base, and that's when you have what's known as relocations that happen. I'll talk a little bit more about relocations when we cover the base relocation table. RVA, this is the offset from the beginning of the loaded image, and so you can just think of these are all relative addresses to the base. So in the PE header, it's broken down into a variety of tables. We're going to talk about the first three in a little bit more detail in subsequent slides, so I won't say much here about the import, export, and resource table. But I do want to mention the other four that I mentioned. The exception table, this is for table-based exception handling. So when an exception is going to occur at runtime, then the appropriate handler is going to be searched in this table to see how that should be appropriately handled. Certificate table, this is used for authentic code. So when you have signed executables, information about the signer and the hash, expected hash, is going to be stored in this table. Then there's the base relocation table, and this is going to contain information about what relocations need to be performed at runtime. So relocations, I mentioned that earlier, relocations are when specific addresses are referenced or used in a program. The simplest way to think about this from a source code perspective is, let's say you have a statement like int I equals the address of J, for example, it's another integer variable. That address of J is going to be in the binary, and if the program is mapped at a different address, so I've mentioned there's a preferred load address, if it's mapped differently, well then this table has information about all the locations in the program that need to be updated or relocated. And the nice thing is that the loader doesn't need to know how these addresses are used. It just needs to know pointers to where are the different offsets that need to be fixed up. And so it will just go through and fix all those up, and the program works. You can read more about relocations on any number of sites. They'll kind of explain the process in more detail about how that works. There's also a thread local storage table. This is, so when you have threaded programs, in particular if you've, like on Windows, there's a decal spec thread where you can allocate thread-specific variables. When you have an entry like that, it's going to add an entry to the thread local storage table, and so when the thread is loaded, then there'll be memory allocated in the heap for storing the thread-specific variables. So these are just some, it's not meant to be a comprehensive list of all the tables, but some of the most common ones that you're bound to encounter. All right, so let's talk a bit more about the import and export tables. The import table, this is for when, from your program, you're referencing functions that are stored elsewhere. So most commonly in a DLL file, for example, you're using API functions, then your program is going to have an iData section, and that iData is essentially a lookup table for the functions that your program is dependent upon, relies upon at runtime. These can be imported by ordinal or name, and then you have the export table, which is essentially the opposite. So the DLLs that you may be dependent upon, those will have an export table entry, an eData section, and again, these will be exported by ordinal or name. So these are two important sections you'll see a lot, and from tools like IDA, for example, there's specific views or subviews that you can load if you want to examine these two tables. There's also the resource table. This is going to contain things like images, dialog boxes, other resources that your program is going to use. If you've done GUI development, then you are familiar with different resource items when you're constructing the GUI that are going to be put into this table. It's a bit more complicated to parse than some of the other tables, so I'd recommend consulting a reference if you want to actually get into parsing this yourself. There's also some API functions you can use, Windows API functions for reading data out of this table. So if we just want to look at some imported functions from common libraries, this is the MSF PE scan tool. This comes with the Metasploit framework. There's many tools you can use to examine the header, so this is just one of many. There's also a lot more that you can do with this tool than just look at imported functions and whatnot. But this just shows you here's some libraries that programs depend upon. You can see the ordinal numbers and then the actual name of the functions that are called by that. Down below, you also see a reference in the section header, these UPX sections. UPX is a universal packer, and you can read more about that online as well, but sometimes malware or other programs may be compressed or packed, and if you see something that's compressed or packed, you know what was used to pack it, then there's pretty much an unpacker for every packer that's out there that you can easily find. I'll talk a little bit more about that later in this lecture. So let's take a closer look using Ollie debug. If you want to use Ollie to examine the PE header, you can click on the modules button once you've loaded your executable. That's the M on here, the arrow's pointing to. And when you look at the memory map here, you can see the clearly labeled the PE header. Also on here, you can see the access these, so this is a read-only. You can see the other sections, the code, data, resources, and the associated permissions that are allowed for those. Okay, so let's say you want to examine that a little bit closer. Well, if you click on the view the PE header dump, Ollie does you the nice service of showing you all the different fields that are part of the PE header. And so if you were to pull up a spec, you'd see all these references. So for an explanation of what each of these refer to, I'll defer to the online resources that you can find. But the this is basically parses it for you and fills in the data, so you can kind of go through there and see what the different fields mean. But this is really handy if you just wanted to kind of examine to see, well, what is in the header, especially if you suspect. I mean, not often do you will you always be looking at the header in reverse engineering. But if you have reason to believe that a file may have been manipulated, compressed, or there's something suspicious happening in the header, well, then this gives you kind of a starting point to kind of examine those fields in more detail. So I mentioned compression earlier. Oftentimes when you do have packers or tools that compress files, you'll see they may leave little trails behind. Like in this case, it clearly even says in a comment that it was compressed by particular packer there. So this just gives you a kind of a clue that you can then go search and try to find a decompressor for this. All right, so now we'll move on to ELF. Again, this is the executable file format for Linux. Same format's used for shared objects, relocatable objects, and executable images. The difference there, shared objects are kind of analogous to the Windows DLLs. Relocatable objects, these are, if you just compile to a .o file under Linux, you'll get these. And of course, fully executable are going to be like your command line type tools that you're running from the command prompt. So the ELF header is laid out. There you have the program header table, section header, describes the different segments and sections. Similar information, again, that we talked about in the PE, but there's definitely some differences. But the best tool for exploring ELF in more detail is what's called readelf. So you can run readelf on whatever executable you want, and it prints out in nicely formatted detail the different fields and what they correspond to. So here we can kind of see it's a 32-bit ELF image, little Indian, Intel 803386 target, and so if you want to explore more about ELF, then check out this tool, and the different options. So it has different command line options to show you different pieces of information about the program. So you can use that to explore ELF in more detail. And that's it. So like I said, this is just meant as a brief overview of the two main file format types that you're going to encounter. I'd encourage you, if you're interested, try loading different programs under IDA or OllyDebug, use readelf and these other tools, and just kind of get a feel for how what information is actually stored in the program. And if you're feeling ambitious, you could even try writing your own PE parser or ELF parser if you want to mess around with some of the actual data structures. So that's it. If you have any questions, just as always, feel free to email us and ask. Thank you.